So I'll take a problem here, which is the salary data set. This is the data that I've downloaded. Ignore the other file. We are going to build it again. So let's have a look at the salary data set. It's a very simple problem. I'll wait for this to open and then I'll explain. Yeah. So I've opened a CSV file as a comma separated value file format. The first column here is just I don't know, it's just serial number. Yeah. So I have about from 0 to 29. So I have 30 records over here. You can see it's a tabular format. CSV can be interpreted as a tabular format. The whole problem statement here is that I want to know what could be the salary of somebody based on their years of experience. Yeah. So I'm going to address that problem. I'm going to create a prediction model that's going to answer that question for me. But I need some data to work with, and this is the data that I'm going to work with, right? It's very less, it's very small, it's only 30 records. But for the purpose of just understanding what linear regression is and all of the associated tests and values to evaluate the quality of the model, to understand those concepts, we are going to use it. Okay. So, years of experience. Um, it could be 1.2, 1.4, 1.6. And since we can see all of these values quite clearly, let me zoom in over here and see, I just make sure that it's visible to everybody here. Um, there are not many values. I can just eyeball this and see that, okay, 10.6 is the largest years of experience value, whereas 1.2 is the smallest, and for salary as well, right? Normally, what I could do is, let's just look at these steps here, right? I've stated the business opportunity, the problem, right? Yes, salary depends on a lot of other factors like where did you work, what kind of industry, what kind of profession or vocation. It's not just a plain function of years of experience, but the thing is, I want to keep it simple over here and just explain a concept and understand the concept. So, quantification, okay, maybe I want to do it uh, with a mathematical model or a machine learning model faster than a human could tell me, right? So as long as I achieve that outcome, then I've quantified it pretty fine. Data acquisition, we have the data. Data inspection, right? So let's perform this activity here. Okay. Format, it's a CSV format, comma separate values. That's the file that I have. You know, what does each data point represent? What is the granularity, type of data? How does it look on a chart or a plot? All of that stuff. Okay, so it's like the serial number, you know. This for me is categorical data, but it's nominal actually. It's nominal data because it just indicates the serial of each. It does not say that serial number 8 is bigger than serial number 2, right? 8 and 2 have no comparative values. So there is no order, no ranking amongst them, right? So this is nominal data. Years of experience, I would say, is continuous numerical data. Yeah. Because 1 year of experience is obviously lesser than 4 years of experience. So there is a certain ranking and comparison that can be done. And same for salary, right? This is all continuous data. So normally, if you want to address a problem where the thing that you want to predict, which is salary, is continuous data, regression is a good choice to do it for such a simple problem. Okay, so you could actually think that, I want to do something fancy. I'll just pick up this file, throw it into ChatGPT, and ask it to do a job for me. Look, at the backend, ChatGPT will probably do something similar. Yeah. If you have a lot of data, then, LLMs, actually, generative AI might start charging you at one point if you want to do this repeatedly. So you'll have to pay a price, right? So whatever solution you want to use is up to you. For me, it's a pretty simple, straightforward problem, to pick a boulder that is just 10 kilograms in weight, I could do it myself. I could do it with the help of somebody else and pick it up and put it aside. For a 10 kg or 12 kg boulder, I'm not going to call an entire forklift to come and pick it up, because one, it's going to take too much time. Second, it's too much money to be paid to the operator of the forklift. So for a small problem, I don't want to have a solution that is overkill. You don't want to do that, right? So that's why I choose linear regression for this. Some terminology to be addressed. The thing that I want to predict, the salary, is called the dependent variable because it depends on the years of experience. I mean, it's just plain language over here. Years of experience is called the independent variable because there is a certain assumption that it does not depend on anything else in this data set. All right, least of all with any other value. So the thing that I want to forecast or predict using machine learning or deep learning is called the dependent variable. And what I'm going to use to do that, to perform that action, is called the independent variable, right? So in other terms, I might just say that salary is, the thing I want to predict, and years of experience is the predictor variable. I could say that as well. Secondly, for those who are new to technology, data, etc., this is a table. Uh, Columns are vertical, B and C. So years of experience, salary are called columns. They can also be called attributes or features in AI parlance. And anything that's horizontal, like a combination of serial number 1.4, and this 46206 value, this is called a row. It can also be called a record or a tuple, right? So that's a short explanation of the tabular data we are seeing, right? A very, very good habit to have is to not work directly on the data that we have, right? So I'm going to close this for now. I don't want to work directly on this data because, God forbid, if I make a mistake, I accidentally change something in the source data, that change is made. Maybe I cannot undo it. Okay, in Excel, I do have the Control Z option, but uh, practically speaking, when you actually work on machine models in in live environments, you want to be as careful as possible not to make mistakes on certain data sets. I'm going to create a new Excel file over here, right? I'll call it salary predictor. Did I type this right? No. Okay, salary predictor. And I'm going to create a query to pull the data from the CSV file into the Excel worksheet. And then I'm going to work on that. For now, I'm just going to open this. Yeah, so I have this Excel over here. What I'll do is I'll go to the data tab. I'm going to click on from text slash CSV because my source data is a comma separated values file format. So I will click on that, wait for it to load. And Excel will open this for me, and I'll have to go to, yeah, salary data set. I will import this. What Excel is going to do is it will automatically make a connection to that file and create a query to import the data, right? So that's what Excel is doing right now. Here is a small preview of the data set that I'm going to query. Yep. It's automatically identified the delimiter as comma. Sometimes the delimiter is a colon or a semicolon in some file formats. That is the inspection that you need to do, right? Before you actually go about doing this. So that's the data inspection part. I've made the query, the connection with the CSV. 30 rows have been loaded. 30 rows were what we saw as well. So I think this is fine. It's good to go. First column is not named in the original CSV, so it's just column one by Excel. That's what it's been named. So we'll just let that be. It's not the column number, or the serial number is not a factor for the salary. It's just a primary key value for all we care. but we are looking at two things here: years of experience, the independent variable, and the salary, the dependent variable. Next, since this is not much data, I can just draw a chart over here. I needed X versus Y, so let me just go to recommended. Yeah, okay, I think this is fine. It's showing me. Okay, so we have this here. Um, Years of experience versus salary. Let me just see the. I need the access titles. So, uh, okay, so this is going to be the years of experience. So I'll put YOE here, and here I'm going to put salary. Cool. So let me zoom in here a bit. Right. So if you have a very large data set with thousands and tens of thousands or hundreds of thousands of records, then you just want to pick up a small sample of that data set, a random sample, and plot a graph. Anyway, you can see that, okay, this is one of the prerequisites of plotting a linear regression model. And I think I have those written here somewhere. Yeah, prerequisites, right? So, oops, it's here. Yeah, so this is the first prerequisite, linear relationship of data. All right. So the thing is, if I want to implement a regression model, right, it could be linear or non-linear. Uh, if it's linear, I need to see if the data is linear. So this is the first thing. If it's not that kind of relationship, you plot a chart and see that the data points are kind of wavy, going up and down in certain regular intervals. Like it's seasonal data, for example, you might want to take a triangular function, or you might want to take a sine or a cosine function to plot your regression. So that's why it's important to visually see what you are dealing with. So you have salary here versus, and you can see that the points are arranged in a linear fashion, and it's a positive linear relationship, right? Means that the smaller the years of experience, the lesser the salary, and the greater the years of experience, the more the salary. Assuming this blue line, if the points were arranged in this fashion, where, for example, the age of a car, for example, yeah, it's a standard car. I'm not talking about a Rolls Royce, but maybe a Hyundai, Honda, Suzuki, or something like that. Yeah, commercial car. With the age of the car, its resale value is going to decrease, and the younger the car is, the resale value is going to be higher. So, in that kind of an example, it's a negative linear relationship between age of the car versus the resale value of the car. So, that's something to be observed. Anyway, prerequisite number one is satisfied over here. The points are kind of in a linear increasing fashion. So we'll use linear regression, right? So I think we've done a bit of data inspection here. Some other things in my data set, there are no zero or missing values. So that's a good thing. And I don't suddenly have text values here. So data quality is important. It's not like I had something like salary has not a numerical but a text value in row number 10 over here. It's not like that. Huh? So it is what we expect it to be, a continuous numerical value. Salary is all integer values, but it's okay. User experience has one significant value after the decimal at best, so that's fine. And yeah, we're going to assume it to be a regular decimal. Yeah. So like 1.6 means 1.6 years and not 1 year, 6 months. No, that's not what it is. Okay. Cool. So data inspection is done. So let's have a look at the AI modeling framework again. We've inspected the data. Uh, it wasn't too hard in this case. Naturally, in live industrial applications, it's going to be much harder. We're looking at cleaning and preparation. It's a data set I downloaded from Kaggle, so it's clean data. There's no cleaning to be done. Like I just showed you, There's no missing value. All of those values are consistent in the same format. They're all numbers, all fine. And there's no data transformation that I need to do. Um, you see, data cleaning and preparation actually also has one more thing, split into training, validation, and testing data sets. Right? This is a non-negotiable practice in building AI models where you need to take a larger subset of the data you have as training data to build the model. And then the smaller subset is going to be used for testing the model, right? For now, let's keep it simple in this example. I'll take 80% of this data to be training data and 20% as test data, right? After I build the model, I'll test it on the test data. So before modeling, let me do that, right? There are several ways to do it. It's just Excel. I want to keep it simple. So I want to create a new column called randomizer over here. And I'm going to use the Excel random function to populate some random values, right? And then I'm going to sort based on the random values to then see what I want. I'm not just picking up the first 80% of values for training data because then my training might get biased a little. I want it to be randomly shuffled for best results, right? So the problem with the Excel random function is that every time I perform any action on Excel, it changes. Just observe column D. Yeah, just have a look. I'll type something in F and I column and I click enter. See, all of the values in random D have changed. So that's a drawback with Excel. If I delete this text that I typed, again, everything changes. So what I'm going to do is I will select all of these values. I'll do Control C to copy. And here I'm going to do a paste special. I'm going to paste the values. Okay. So, and let me save. So now you can see that column D does not have the function random, but it has the actual values. So now if I type anything in another cell, the values are not going to change. Yeah. No matter what I do. I type, I delete, it's not going to change. So now I'm good to work with this. With the randomizer, I'm going to sort smallest to largest. I'll keep the last 5 rows as test data, and up till then, I'm going to use it for training, right? So these are about, oops, okay, 25 rows are going to be training data and 5 are going to be test data, right? So let's see how that works. So now let's do one thing. I'll copy this salary data set. I'm going to create a copy, right? I'm going to call this training. Okay. And last 5 rows, right? From here. I'm going to delete these. I'll copy the salary main data set again and create a copy. And I'll call this test data. So we are not going training, validation, and test right now. We'll do it with larger data sets. Here we hardly have 30 records to work with, so it's going to be overkill for now. Uh, anyway, we have test data. I want to keep the last 5 records over here. So all of these, except for the labels, I'm going to delete. Right. So, okay. So I've done my training and test split of the sample. Now it's finally time to run the regression model. Okay. For that purpose, I have already installed the Excel Miner toolpack on my Excel. You can just Google that. It's free. It's free. It's provided by Microsoft. It's available in the Microsoft Store. Just go on and download the package and install it on your PC. It's going to be very simple to do. If you have a Mac, they have an installer for Mac as well, right? For Mac OS. So no problems there. You can download for Mac OS also. Anyway, I have the show toolpack option here and it opens all of this. So you can see there are all of these basic statistical analysis tools like correlation covariance tests. I have t-tests at the bottom. I have ANOVA tests, which ANOVA stands for analysis of variance. I don't need to do it separately. As I run my regression analysis, I'll get an ANOVA table as well. So I'll show you how it happens. Um, and then we have we can create a histogram also. We'll have a look at that as well a little later. Um, for now, we're looking at linear regression, right? So, okay, so now in the training data, I don't need the randomizer. In the test data as well, I don't need the randomizer. This was just to split the sample in the beginning. Okay. Okay, I opened linear regression in the training data set, Y range and X range. This is terminology. Y range stands for the dependent variable, as in the value that we want to predict. X range stands for the independent variables, right? The predictors. So in our case, Y range is going to be simple, column C. And X range is going to be column B, since we have only one predictor variable, right? So that has been correctly taken. Labels, yes, I have selected the labels as well, user experience and salary, which is row number 1. So constant is 0. Let's not bother about this option at all right now. Confidence level 95%. Usually, one other prerequisite of regression is that the data should be normally distributed. A normal distribution curve is something simple that you can Google and find out about. But the confidence level is usually associated with that kind of distribution, right? For now, let's keep it simple over here. 95% is usually a good thumb of rule value to take over here. And we'll discuss the mathematics of it in a different video or a short separate, right? For now, it's a simple problem to solve, and we'll just go with this. Output range. I want the results of all of these output somewhere. So let me put that here, right here, E3. Okay, and from starting from here, output will be printed from E3 to the right and bottom. Okay, so I don't mess around with the table on the left. We have some other options here for linear regression. Residuals is a set of the uh, error values between the actual and the predicted values from our regression modeling. And then we have plots, standardized residuals. We don't need all of that. Normal probability plots. We don't need all of that. But residuals I'll select because it may be useful to explain one or two concepts later. Yeah, so let me just select that. The rest is, I think we are discussing applied data science, machine learning. Our objective is to create a predictor model. So we'll keep it simple for now. I click OK, and Excel Miner has instantly output all of this. Right. So to start with, I have this. We have these regression statistics. We have an ANOVA table, analysis of variance, and then I have the regression output as well. Yeah. And then I have the residual output at the bottom. Residuals are to do with each data point. So you can see that there are 25 of them, right? Because our training data has 25 values. We just did that. We selected as many. Okay, so our summary output has all of this. Now, the question is, there are two questions here, right? How am I supposed to read the regression statistics and the ANOVA table to make certain judgments on the predictor model that I have created? And that's the first question. The second question is, how am I able to create this prediction, right? What is the model? Is it something that a genie gives me when I rub a lamp? Or is it something very abstract that I cannot visualize or find out? No, it is simple linear regression. It's going to be the equation of a line. And what are the variables we put in the equation of a line is given to us by this table over here, especially the coefficients. So I'll get to that in a bit, right? In fact, actually, let me do that first and then I'll go explaining the other stuff. So I have this here. I'll just put it here. Y equals mx plus c, right? So This is the, I should highlight this. Nah, that's a bad color. Yeah, this is good. Okay, I'll highlight this, increase the font a bit. Y is equal to mx plus c, right? Uh, like I explained, we saw the plot earlier, right? So it's a linear relationship. So what linear regression does is it's going to create a line through those points. So that is the predictor. It's just a simple line in Cartesian geometry. The equation of a line is y equals mx plus c. Now y and x are the variables. We already saw in the linear regression option on the Excel minor tool pack, like I showed you here. Let me show you again. Input y range and x range, right? So y range is the salary that we want to predict. X range is the predictor. X is the years of experience. So that's what it is, right? Even in our line equation, y is the salary, x is the years of experience. So using this line, what I want to do is if I put a value for x, saying that, okay, 5 years of experience, that's the value for x. I know the values of m and c from this, and I can calculate the value of y. So you see, that is the predictor that I have created. This, my friends, is uh, the most simple form of a machine learning algorithm, right? It's nothing but a simple line. It's mathematics, right? So it's nothing too complex. Anything that we are going to explore, that even I am going to explore and study, and I hope you will with me as well. Anything else is just an extension of this, right? It's going to be maybe a slightly longer equation, more complex equation. Maybe from linear, it's going to be a quadratic equation in future. It depends on the data that you have. But this is exactly what it is, right? It's nothing but a mathematical equation. You plug in some values you know already and find the unknown value. That's all it is. Okay. So what are M and C, right? M, in fact, M equals, let me align this. M, right? You know what this is? This is the slope which is given by the coefficient of years of experience. Why is my function key not working? It worked. Okay. Thank goodness. So, okay. So M is equal to this, and C is the intercept. Now, it's not very difficult to guess that I'm going to click on this. And F4 is going to anchor my value. And yeah, that's what I have. I'm going to bold this, and I'm also going to highlight these as well. All right. So you see, I have this now. Now let's evaluate all of this. So we have this, we have M, we have C in the equation. So anytime you see, I have my predictor, right? So for example, if years of experience is 5, salary equal to, let me just write here, sample. If years experience is 5, salary equal to, going to say equal to this into 5, yeah, plus C. Yeah, that should be it. Right? The salary should be 70,946.34. So this is what my machine learning model gives me based on linear regression. Right? Let me highlight that as well. So yeah, this is what it's supposed to do. Predictors and models are not perfect, right? They need tuning, they need performance optimization, right? There are some trade-offs that we need to deal with before we finally settle on a certain prediction model, right? Um, I could possibly maybe say that no, I don't want m equals 9131.662, right? The slope should actually be 9131.7. Maybe I want a slightly higher slope. And the intercept correspondingly, I want it to be 25288. That's it. No, nothing after the decimal, right? Maybe if that's the choice I make, based on some observations, then that's going to be my y equals mx plus c. That's going to be my linear regression ML model. In that case, the salary that's going to be output will be according to that, right? But how do I make these decisions, right? For such a simple model, there's not much to actually look at. But there are some performance parameters to be tuned, to be observed first, right? So we are going to have a look at those two. There are many values that we saw that were output as a result of running the linear regression, right? And those boxes are highlighted. Some of the important ones are here, right? Since this is something that involves, in our example, just one dependent and one independent variable, it's simple linear regression. So the R squared value is good to tell us how good the model is, right? So it's a proportion of variance in the dependent variable as explained. So it's between 0 to 1. The higher it is, the better fit the model. Something, that's 0.9 and above is a good value for R square. It means you can be really sure that the model is a good fit. Multiple R is, something that it's the square root of the R square, right? It's the square root of R square. So multiple R actually ranges from -1 to +1. Yeah, so this has negative values as well. So 0 means there's no linear relationship, there's no linearity. So in case the multiple R is a very small value whose amplitude is close to 0, then it means your data set is not really linear. But in our case, it has a positive linear relationship as is on the graph. So, it's going to be a high positive value. A negative linear relationship will be a lower negative value that is closer to -1. So if we took the example of the resale value of a car based on the age of the car in years, then that's going to be a negative linear relationship, and the multiple R is going to be like something like maybe -0.75, -0.8, or -0.9, right? So it's going to be in that range. Adjusted R squared, in our example of simple linear regression, R squared is enough for us to evaluate whether the model is good or not. Adjusted R squared is good for multiple linear regression, which is the topic of the next video that I'm going to make. So I'll take an example for adjusted R squared to use to evaluate a model for multiple linear regression, and I'm going to use the graduate admissions dataset to do that. Also available on Kaggle. Then we have p-value. This is something we're going to see, and significance f, right? So p-value gives me information about each predictor variable, about each independent variable. How good is it at predicting the dependent variable, right? What is the value of each? Right now in simple linear regression, we just have one. So, that's all we have to work with. So the p-value in simple linear regression is not going to be of much help because that's the only value we have to work with. So it's more useful for multiple linear regression. And significance f is also overall p-value for the overall model. How good is the fit? And then we have standard and residuals. The definitions are here. Will not, practically speaking, for regression models. These are further details, right? To have a look at each data point. Coefficients and intercept, I have already shown you how these are used to construct the linear regression predictor equation, right? So that's why they are in a different color. So here, I'm just going to highlight the very basic few values that are useful for us to evaluate how good the model is. So if you look at the R squared values, it's 0.96. So it means that this model that we have created is a very good fit. 0.96 R squared is more than enough for me to say that, okay, I'll go with this. I don't need to tweak this model anymore. Okay. If you were working with some value like 0.82, 0.85, it's still good. It's not bad. But maybe if it's a complex model, that kind of R square value tells me I still have some scope for improvement to get it over 0.9. And maybe there are some parameters in the model that I can tweak, parameters and hyperparameters, right? These are concepts that we'll discuss with more complex ML and DL models in later videos. So R square is already good here. Then the ANOVA table, like I said, adjusted R square in simple linear regression is always going to be very close to R square anyway. So it's not much more that it tells us. ANOVA table here is, these are degrees of freedom. This is sum of squares, which is actually the distance of the actual, salary values versus the predicted values. So it's like uh, the error term actually. Then you have the mean squared values. This is the mean of all of the error terms, right? And then you have the f value and then the significance f, right? Which is 0. So for us here, normally, I'd say, yeah, f value and significance f are good because as we look over here again, significance f is overall p value, right? Tests if at least one predictor is significantly related to the response. Now, this is simple linear regression. We actually have only one predictor, right? So, significance f actually has no option but to agree with us over here, which is why it is 0, right? In multiple linear regression, we'll see how this becomes more important. So, we can look at this. It is good. We looked at the coefficients. Let me highlight these as well. And we've already used them to construct our predictor p-value. P-value is important here, right? So the p-value actually tells us how effective is each independent variable in predicting the salary, right? So yeah, we have just one variable, years of experience, but we also have the intercept, right? Which is the constant value generated. So p-value, as a rule of thumb, if it's equal or lesser than 0.05, great, excellent. It means your corresponding independent variable is a very significant predictor of the outcome, right? It means its role is statistically significant. It means years of experience. Okay, so you see here, right? It's a very small value, 6.56 and exponent to the power minus 18. So I mean 0.0000 around 17 zeros and then the 6 starts. So it's way, way smaller than 0.05. Years of experience, therefore, is, we can safely say, years of experience, therefore, is very effective at predicting the salary in our model, right? It is going to be very significant. So if the years of experience changes, the salary changes. And we can correlate with our observation. We saw the graph, all of the data points were quite well arranged. So we already could see it visually as well, right? So the mathematics over here confirms our visual inspection. Intercept also is a very small value, way smaller than 0.05. So yeah, this is also statistically significant in our model, right? So the C value over here in y is equal to mx plus c is significant. So that's what the p-value tells us. But if the p-value was something like 0.1 or 0.07 also, that's greater than 0.05. So in that case, the corresponding independent variable or the predictor can be said to be not so effective at predicting the outcome. Okay, so we'll see that in some other examples that we tackle later in other videos. So now that we have discussed the significance of all of these statistical factors, we have to realize that we have been looking at all of these from the point of view of the training data set, right? If we go back and look at the AI modeling process, we have to look at the refining and the testing stage. So in our case, let's just have a look at the testing stage. We should run this model on the test data and then see how good is it fitting the test data, right? So we need to look at the, at least let's look at the standard error on the test data for this model, right? So this is our equation. Let me copy this and I'm going to paste it somewhere far. Let me do it here, right? So this is what we have. Oops, I should have pasted the values. Huh? Yeah, I just paste the values here. Good, got it. I think this is good enough to go. And I will highlight it a little bit so that I know that this is there. Okay, so now I'm going to look at the predictions, right? So I have to do things by hand in Excel. Uh, it's a drawback of this tool. Anyway, we have this. It's a simple thing to type a formula over here, mx plus c. So m is here. Let me anchor it. Multiplied by x is the years of experience. I'm going to add the constant c, which is the intercept, and anchor this as well. Right. So these are the predictions that I get for the testing data. And now I need to look at how good the predictions are, right? So there are two ways to do it. Since this is just very simple data, it's two-dimensional data. I can plot a graph and see it. But for multiple dimensions data, you can't do that. And therefore, you have to rely on mathematical methods. But for now, I think we can actually insert a chart. I'll do one thing. Let me create scatter plot. Yeah, this is good. Okay. And here I can see that the blue dots are the salary, which is, the actual values versus the orange dots which are predictions. Not bad actually. Not bad. Yeah, they are quite close, except for maybe two values for 6.1 years. So we have this one, value number 19 over here. There's a larger variance. And we have this one, value number 23, where there's a larger variance, but for the others are pretty close. This is 2D data, therefore I can make that evaluation visually, right? But how do you do it mathematically? We rely on a concept called sum of squared errors, or better still, the standard error for the test data set, right? So it's just a couple of steps. The thing is that if you look at it visually here, the error is basically the difference in the salary versus the predicted salary values, right? So you just need to subtract them and see the difference. Also, if you subtract them, it might be a positive or negative value. So one step further, we are going to square it. So it's going to be the square of differences, right? So I'll say SE, which stands for squared errors. So it's going to be square. What the hell? What's the formula for square in Excel? Uh, anyway, we have predictions minus salary. Oh yeah, we have the hat symbol over here. Yeah, okay. So we have this now, which is the squared errors between salary and predictions. Right. The next is that we have the squared errors. So I think this is like for each data point, right? So we have the squared errors. We want to see the standard error for the entire test data set, right? So what we're going to do is we'll add all of them, and we are going to divide by the degrees of freedom. So, normally the degrees of freedom is equal to, you know, count all of these, subtract by number of, so number of predicted variables, which is one, and it's minus one again, right? So it's a n minus k minus one formula where n stands for number of data points, and k stands for number of dependent variables, and one is, I'm sorry, independent variables, and one is just one is constant here. So normally it's n minus 2 for linear regression, the degrees of freedom. So it's 3. So here what we need to do is have another column, sum of squared errors, where it is going to be, oh yeah, this shouldn't be part of the table. Sum of squared errors is equal to sum of this entire thing, so that is what it's going to be. Have the sum of squared errors. I'm going to divide it by degrees of freedom, and then square root it to get the standard error for this test data. So finally, we're here. So this is going to be a square root of this value. Let me anchor this, divided by the degrees of freedom, which also I will anchor with dollar signs. And yeah, this is the standard error of the entire estimate that I have. So I will highlight this in green, and let me increase the font as well so we know. Okay, we have this value here, standard error, which is 11526. Now, generally, there is um, no thumb rule regarding the value of the standard error, saying, how much is good or how much is not. You know, all I'm saying is that it's up to your judgment. So I'm saying that 11526, if you compare it to the salary values which are normally, above 90,000 over here, to, above 100,000 to 110,000, 120,000. This is just about, 10% of those values. So, okay, I mean, it's not very small if I compare it to the actual values. The error is not insignificant, but the thing is that this is what we have based on the model we trained. So, I think this is okay to go with. If the standard error were, more comparable, like 20-30% of the predictions or the salary, then I'd say, yeah, that's a really big value for the model. So overall, I think based on standard error, at least I can say that this model is performing fine with the test data set. And if there is anything to be improved, then I'll have to tweak the parameters of this model, which is right here, M and C, the slope and the intercept. And it's a very simple model. It's a line. You have just two parameters. There's not much you can adjust over here, right? So there's not much you can tweak. I will not be able to optimize it so much that the standard error goes from this value to something like 5,000. No, I mean, that's not going to happen over here. But in more complex models, the parameters and hyperparameters can be tuned with more flexibility and freedom to improve the fit of the model to the training or the test data. So that is something that we'll explore as we go ahead and see. So I think uh, this is good enough to demonstrate the process for now, as to how do you uh, create a basic machine learning model and train it on training data, test it on test data, and see how well it fits. So I think that's good. It concludes our first inspection of very simple statistics, and applied data science in constructing a simple linear regression model for one dependent variable and one independent variable. And thanks for bearing with me. I hope you were able to follow through, and just go on to Kaggle, look for this salary data set, and you'll be able to download the same data that I have. And if you want to practice, just follow the steps that I have. So yeah, all the best. Keep watching, and see you in the next video.